The next talk in our session will be titled Stitcher Shape, Bottom-up Learning for BREP Generation. And the authors are Pu Li, Wenhao Zhang, Jinglu Chen, and Dongming Yan from Chinese Academy of Science. And the presenter will be Pu. Please take away.
Hello, everyone. My name is Pu Li, and I'm presenting our paper Stitcher Shape, which introduces a bottom-up approach for BREP generation. CAD generation is mainly aimed at improving the efficiency of manual modeling or reverse engineering for designers. CAD data representations fall into three main categories. First is CSG, which combines basic geometric primitives using Boolean operations. Second is modeling command sequence, which formalizes a model's construction history as a parameter sequence. Third is boundary representation, which is our target output. Boundary representation models object surfaces through vertices, edges, and faces. When comparing these three representations, BREP stand out with superior expressiveness and the largest available dataset. If we compare BREP with common 3D representations like point cloud, voxel, and mesh, BREP offers distinct advantages. First is the most compact representation, with only 9 faces in this example. And BREP also provides exact geometric representation based on parametric definitions, while other formats are limited by their discrete resolution. However, these advantages come with challenges. BREP has the most complex data structure with two difficulties: irregularity and hierarchy. Irregularity means that both the type and the quantities of geometric elements can vary. For example, these three faces have different surface types and contain different numbers of loops, edges, and vertices. Hierarchy means that in BREP, vertices, edges, and faces are connected in a hierarchical graph structure. These three levels affect each other, and it's hard to break them down into separate pieces. BREP Gen, a paper from last year's SIGGRAPH, offered a solution to these challenges. First, to deal with the different surfaces and curve types, they proposed not to generate the parameters directly. Instead, they uniformly sample points in the UV space and learn to generate these points. Then they feed this point back to the spline surfaces or curves. This way, they solve the problem of inconsistent surface and curve types. For the hierarchical problem, BREP Gen proposed converting graphs into trees. You can see that the pink edges and all the vertices were duplicated. To further handle inconsistent number of elements, they used repeat padding. While this solved both the hierarchy and the inconsistency issues, it led to many duplicated geometric elements. For example, this local shape with 2 edges and 3 vertices would be expanded to 6 edges and 12 vertices. The cause of the duplication is that BREP Gen adopts a top-down approach from faces to edges to vertices. If we flip this around using bottom-up generation order, such duplication can be avoided. Bottom-up generation means that we first generate vertices, then curves, and finally faces. If we break it down further, we can divide it into 6 steps. First, we generate vertices, then learn about connections and curve geometry. Next, we need to identify which loops should be filled, classify inner and outer loops, and finally learn the face geometry. These 6 steps form our complete pipeline. Let's explain this from left to right. First, we need to generate vertices. We use a transformer decoder to autoregressively generate the XYZ coordinates. This is a standard decoder-only architecture, and I won't explain it in detail. For conditional generation, we can add condition tokens at the beginning of this coordinate sequence to control the generation process. After generating the vertices, we need to learn how to connect them. We first use self-attention to extract features from each vertex. These vertex features are paired with each other and pass through an MLP, which determines whether the vertices should be connected. For example, we combine the first vertex with each remaining vertex to determine its potential connections. This process is repeated for all vertices. The result is a connectivity matrix that defines the graph structure of connected vertices. Also, we can add condition tokens at the beginning. Given this connectivity graph, we need to identify which cycles should become phases and which should remain empty. To do this, we first detect all possible cycles and arrange them in a sequence. This sequence is then processed by a transformer encoder for binary classification to predict which cycles should become phases. Those identified as phases undergo a second binary classification through a similar network to distinguish between inner and outer loops. For the subsequent tasks, we use the same network, so I will just describe the input and output. For curve mapping, the input is an age sequence and the output is a curve sample point sequence. For phase mapping, the input is an loop sequence and the output is phase sample point sequence. Using the generated vertices, curves, and phases, we construct the final BREF model through a geometry modeling kernel. Here are some examples demonstrating how our method handles ambiguity. In the top left, we show how identical vertices can result in different connections. The top right illustrates the same connections can form different loops. The bottom left shows identical loops resulting in different curves, while the bottom right shows identical curves resulting in different phases. Here are the comparison results for unconditional generation. Our generated results shown on the right include BREF models with conical vertex and thin plate shapes. Besides the generation quality, it's worth noting that our method significantly improves generation efficiency. As shown in the table below, compared to the diffusion-based method, our approach requires much less time. Here are the results of conditional generation on the furniture dataset. To achieve this conditioning, we simply prepend a category describing token at the beginning of the generation sequence. Here are the auto-completion results. Each example shows different results generated by our method conditioned on the bottom shape. We also generate BREF containing multiple connected components, which is difficult to handle with previous method. We can also generate other similar structures such as n-gon mesh. Our approach has some limitations. First, we only handle simple graph structure, so we need to add additional vertices to avoid life cycles. Secondly, the computational complexity of the connectivity module is n-squared. So when the number of vertices increase, it's hard to learn the correct connection. To address this issue, one may look at some recent work in wireframe generation. Finally, our pipeline consists of 6 networks, which may lead to accumulated errors. Future work should focus on designing more concise representation or networks. Well, that's all of my presentation. Wenhao and I will appear in the interactive session, so welcome if you have any questions. Thank you.